For most of the space age, Mars has been the case we thought was closed, a frozen desert. No air worth breathing, no water that lasts, its rivers dry for something like 3 billion years. The textbook planet you point to when you want to explain what a dead world looks like. Then, on a cold Martian night, a robot the size of a kitchen table pressed a sensor to the dust and simply listened, and the ground answered. Not with wind, not with noise from the lander itself, but with something coming up from far below, something no one was sure was even possible anymore. What that machine heard could rewrite where all of Mars's water actually went, and whether anything down there is still holding on. That was November 2018. By 2024, the same buried silence had given up a secret. But to understand why it stunned everyone, you first have to see how completely dead we believed this planet to be. The red silence. Stand on Mars today, and the numbers alone would kill you. The average temperature sits around -60 degrees Celsius, colder than anywhere on Earth's surface. On a good summer afternoon near the equator, it might crawl above freezing, then plunge past -100 degrees Celsius once the sun drops. The air is barely there. Atmospheric pressure is less than 1% of what you feel at sea level on Earth, and it's almost all carbon dioxide. That's too thin to hold warmth, too thin to shield the ground, and far too thin for liquid water to survive out in the open. Spill a cup, and it boils and freezes at the same time before it can pool. With no magnetic shield and no ozone, radiation pours straight onto the plains. Rust-colored dust stretches to the horizon, still and silent under a pale sky. But this graveyard of a world wasn't always this way, and the evidence for what it used to be is carved into the rock in plain sight. A world that bled out. Roughly 4 billion years ago, Mars had a real atmosphere, thick enough to trap heat and hold water on the surface. Then it lost the one thing that was protecting it. Deep inside, the planet's core cooled, and its global magnetic field faded away, and that shield was what had been deflecting the solar wind. The solar wind is a constant stream of charged particles blasting off the sun at hundreds of kilometers per second. With no magnetic field left to steer it aside, it slammed straight into the top of the atmosphere and stripped it away, molecule by molecule, out into space. NASA's MAVEN mission measured this still happening today, escaping at rates that add up over hundreds of millions of years. Bit by bit, the air bled off into the dark. The pressure dropped, the greenhouse warmth leaked away, and the temperate planet cooled into the frozen desert we see now. As the air thinned and the cold set in, the water that once ran across Mars had to go somewhere, and the first place to look is the ground it carved. Rivers in the rock. Look at the orbital images and you can still trace where it flowed. Wide fan-shaped deltas spread out where rivers once emptied into open water, their sediment layers stacked exactly the way a river builds them on Earth. Branching valley networks wind across the highlands like the veins of a leaf, thousands of them, feeding into channels that ran for hundreds of kilometers. The rovers found the smaller tells too. Curiosity rolled over rounded pebbles, smoothed and polished the way stones tumble, only after a long ride in moving water. Nearby, drilled samples turned up clay minerals that form when rock sits soaking in standing water for a very long time, not in a passing splash. None of this is subtle once you know how to read it. The shapes, the sediments, the chemistry all point the same direction, toward a Mars that was wet for a very long stretch of its early history. These channels didn't come from a trickle, they came from oceans, which raises the single question that has haunted Mars science for decades. The vanishing ocean. Add up the carved terrain, the mineral deposits, and the chemistry left behind in the rock, and the numbers get hard to ignore. The best estimates suggest early Mars held enough water to wrap the entire planet in a global layer somewhere between 100 and several hundred meters deep. Spread flat across the surface, that's an ocean's worth of water, comparable to a shallow sea covering half the northern hemisphere. Now set that against the Mars we actually see. The surface today is bone dry, so dry that liquid water can't survive there for more than moments before it boils or freezes away. The riverbeds are empty, the deltas are dust, and the sea that once filled those basins is simply gone. That gap is the problem. Hundreds of meters of water don't just fade out of the record without leaving a trail. An entire ocean does not simply disappear, so scientists lined up every possible fate for it and started crossing them off. Where did it go? The first suspect is space itself. With its magnetic field gone and its gravity weaker than Earth's, Mars couldn't hold on to its upper atmosphere, and water vapor high above the surface got broken apart by sunlight. The lightweight hydrogen drifted off into space, and spacecraft like MAVEN have watched that escape still happening today, molecule by molecule. The second idea keeps the water on the planet just frozen. The polar caps are mostly water ice, and beneath the surface there could be vast sheets and lenses of buried ice, locked away where the cold preserves them. Some of the ocean, this argument goes, never left at all. It just went solid and hid. The third path is chemistry. Water can bind directly into the crystal structure of minerals, chemically absorbed into the rock, so it stops being water at all and becomes part of the stone. Each explanation sounded reasonable on its own, but when researchers added up the numbers, a large fraction of the ocean was still missing. The ice accounting. So the search became an audit. Start with the obvious, the polar caps. If you melted every bit of frozen water at both poles of Mars, you'd get a global layer of liquid, maybe 20 to 30 meters deep. That sounds like a lot, until you remember the ancient ocean would have needed a layer closer to a few hundred meters. Then you add the rest of the known ice. Buried glaciers spotted in the mid-latitudes, hidden slabs the size of small countries, permafrost locked into the top layers of soil across huge stretches of the planet. Add it all together, every confirmed reservoir, and the total still climbs to only a fraction of what once filled those ancient shorelines. The math kept coming up short. The ice we can see and measure and map accounts for perhaps a third of the water Mars is supposed to have lost. The ledger simply refused to close, and that gap pointed attention away from the surface entirely, toward the one direction nobody could see. Locked below, down, not into ice at the poles, not into vapor drifting off into space, but into the body of the planet itself. What if the missing water never left at all? What if it sank, seeping through fractures and pores over billions of years, then bound itself into the deep rock, far below anything a rover could reach? It's a strange thought when you sit with it. An entire ocean, not evaporated, not frozen, but folded into the crust and mantle, stored inside minerals under crushing pressure kilometers down. The water wouldn't slosh or flow. It would be woven into stone, invisible, a fossil sea locked in the planet's foundations. For decades, this was little more than a whisper among geologists, an elegant idea that explained the shortfall almost perfectly. It was a compelling guess, with one fatal problem. No one had any way to look inside a planet from millions of miles away. Reading a dead heart. Here on Earth, we already knew the trick. We can't dig to our own core. The deepest hole we've ever drilled reaches barely 12 kilometers into a planet thousands of kilometers across. So we don't dig, we listen. When an earthquake ruptures, it sends waves rippling out in every direction, and those waves travel through the planet, not just around it. As they pass through different materials, they bend, speed up, and slow down. A wave crossing dense rock moves faster than one crossing something soft or molten, and some waves stop dead at a liquid boundary and refuse to continue. By recording exactly when and how those waves arrive at stations around the globe, scientists reverse engineer what they must have passed through. Every hidden layer leaves a fingerprint in the timing. That's how we mapped Earth's crust, mantle, and core without ever seeing them. On Earth, we have thousands of quakes to work with, but to try this on Mars, someone would have to land a single listening device and hope the planet still trembled at all. The listening machine. So NASA built exactly that. The mission was called InSight, and at its heart sat a seismometer so sensitive it could feel the ground move by less than the width of a single atom. Think about that. A tremble smaller than an atom on a planet 60 million miles away on a good day. To catch motion that faint, the instrument had to be shielded from everything. Wind, temperature swings, the gentle tug of the Martian day. Engineers wrapped it in layers, sealed it under a dome, and tuned it to hold still while it waited for the ground itself to whisper. It was a beautiful piece of hardware, and it carried an uncomfortable secret. A seismometer that senses nothing is just an expensive paperweight on a cold plane. Everything depended on a gamble that a supposedly dead planet was still faintly alive, and in late 2018, that gamble finally came down through the Martian sky. Touchdown at Elysium. On November 26, 2018, InSight hit the top of the Martian atmosphere at around 12,000 miles per hour. It had roughly 7 minutes to slow to a stop, using a heat shield, a parachute, and a final burst of retro rockets. And through all of it, no one on Earth could help, because the radio signal took about 8 minutes to arrive. So the whole descent had already happened by the time we heard it begin. Engineers sat and listened to the past, waiting to learn whether their spacecraft was intact or a fresh crater. Then the flat, boring plains of Elysium Planitia did their job perfectly, and InSight settled onto the dust. The landing site was chosen for being dull. No mountains, no boulders, just a smooth parking lot so the lander could set its instruments straight onto the ground. A robotic arm lowered the seismometer, placed it on the surface, and leveled it with enormous care. The seismometer was down and sealed under its dome, and then, for weeks, the planet gave it nothing but wind. The first tremor. The instrument heard the breeze pushing across the plain and the faint creak of the lander itself, useful for calibration, but not what anyone crossed 300 million miles to find. Day after day, the trace stayed empty of the one thing that mattered. Then, on April 6, 2019, on the mission's 128th Martian day, the seismometer caught something different, a small, rumbling signal that rose out of the noise and faded away, unlike anything the wind could make. It was faint, roughly the size of a quake you'd barely notice standing on Earth, but its shape was unmistakable. It had come from inside the planet. After weeks of silence, Mars had moved on its own, and the machine felt it. That faint shiver was more than a heartbeat. It was a flashlight, because every quake sends waves plunging through the interior and back with the shape of everything they passed. Waves through worlds. Not all seismic waves travel the same way. The fast ones, called P waves, push straight through rock and even liquid, squeezing the material forward and back as they go. Behind them come the slower S waves, shearing sideways, and those refuse to pass through anything molten. So just by timing which waves arrive, and which ones never show up at all, you can start to feel out what lies between you and the far side of the planet. Every time a wave hits a boundary between two kinds of rock, part of it bends and part of it bounces back. A change in density, a shift from solid to liquid, a seam where one layer meets another, each one leaves a fingerprint in the returning signal. From a single lander sitting still on the surface, that's enough to begin mapping the hidden structure below. As the quakes accumulated, the waves began to draw the first-ever cross-section of Mars, and the very top layer already broke expectations. The crust revealed. The models had guessed the Martian crust was thick, maybe 65 to 70 kilometers of solid rock wrapped around the planet. The waves said otherwise. Beneath InSight, the crust ran far shallower than that, in some readings only about 20 kilometers before the signal changed. And it wasn't one clean layer. As the waves passed downward, they kept catching on boundaries where none were expected, each reflection marking a shift in the rock. Something about the density kept changing, step by step, in a way a single cooled shell of stone shouldn't do. The crust wasn't a single slab, but a stack of distinct zones, and the differences between them hinted at a violent, water-shaped past. Layers of deep time. Read from the top down, those layers behave like pages in a very old book. The uppermost few kilometers looked broken and porous, the kind of shattered rock left behind by billions of years of asteroid strikes hammering the surface. Below that sat denser, more solid material, laid down in an earlier, quieter chapter of the planet's life. Each boundary marks a change in how that rock formed and what happened to it since. Fractured, low-density stone doesn't just record impacts. It leaves room, empty space between the cracks, the sort of pore structure that on Earth soaks up and stores groundwater deep underground. Fractured rock miles down is exactly the kind of place a lost ocean could hide. But before that idea could be tested, the waves had to reach far deeper, into the mantle. So the waves pressed on, sinking past the fractured crust into the thick shell beneath it. This is the mantle, the great warm layer that makes up most of a rocky planet's bulk. On Mars, nobody had ever measured where it started or how far down it ran. InSight's quakes changed that, their energy bending and slowing as it passed through rock of shifting density. By timing those bent paths, scientists traced a mantle reaching down roughly 969 miles before the character of the waves changed again. That's a single deep layer, not the nested shells Earth carries. And the way the waves moved through it hinted at rock that was cooler and stiffer than many had expected, a body holding less heat than a planet its age might. The mantle told a story of a planet cooling from the inside out, and that cooling had consequences no living thing on Mars could have survived. A slower planet, a cooling interior sounds abstract, but its effects are physical and relentless. Heat is what keeps a planet's insides moving, softening rock enough to churn and rise and sink. Mars is about half Earth's diameter, and smaller worlds lose their heat faster, the way a coffee cup cools quicker than a bathtub. The seismic readings suggested a mantle that never fully turned over the way Earth's does. Instead of vigorous convection dragging hot rock up and cool rock down, Mars seems to have settled into something sluggish, its internal engine idling rather than roaring. The composition mattered too, rock richer in iron that behaves differently as it warms and cools. A cooler, weaker interior meant one thing above all, and to see why it doomed the surface, you have to look at what stopped churning at the very center. The missing plates. On Earth, that inner heat drives one of the planet's defining features. Our surface is broken into plates that grind, dive, and resurface, constantly remaking the ground beneath our feet. Mountains rise, ocean floor is swallowed, new crust is born at the seams. Mars never got there. The data points to a single, unbroken shell, one rigid lid wrapped around the whole world with no seams to move along. Whatever churning once happened below wasn't strong enough to crack that lid and set it drifting, so the planet froze into a fixed skin that hardened and stayed. It's a stillness that costs a world dearly. Without moving plates, Mars couldn't recycle its surface or its water the way Earth does, and that trapped water had nowhere obvious to go but down. Something deeper. But as the interior slowly came into focus, a few readings refused to sit quietly inside the picture. On a truly dry, dead Mars, certain waves should have moved one way. Instead, they came back softened, slowed, bent in places the models hadn't planned for. It was subtle, the kind of thing you could almost explain away. A slight delay here, an echo that arrived weaker than it should. But the pattern kept surfacing, and it pointed somewhere far below the crust, deep enough that the surface gave no hint of it. Something down there was interfering with the sound of the planet itself, and the more the team looked, the harder it became to ignore the possibility that Mars was still holding on to the very thing everyone had spent decades hunting for. Those stray signals would take years to make sense of. But first, the team had to finish the map, and the biggest blank space on it was the core. The core question. For half a century, the Martian core had been little more than an educated guess. Nobody had ever felt it directly, Everything came from indirect clues: the planet's mass, its density, the slow wobble in its spin, and from those numbers, scientists built models that quietly disagreed with each other. Some argued the core had frozen solid long ago, a cold ball of iron locked at the center. Others insisted part of it was still molten, sloshing beneath thousands of kilometers of rock. And the size was just as contested. Estimates ranged across hundreds of kilometers, each one reshaping the story of how Mars formed and died. You couldn't settle it with math alone. You needed to reach down and touch it, to send something through the whole planet and read what came out the other side. For the first time, seismic waves were about to touch the center of another planet and send back a verdict. Bigger than expected. When the answer arrived, it landed bigger than most models had allowed. The seismic waves traced a core with a radius near 1,830 kilometers, roughly half the width of the entire planet. That's a heart taking up far more of Mars than many researchers had penciled in. And it wasn't the frozen ball some had imagined. The waves that struck it behaved the way they do when they hit liquid, bending and reflecting in a signature that's hard to fake. Deep beneath the cold, still surface, a vast sea of molten metal was still there, still fluid after 4.5 billion years. For a moment it looked like a clean answer, almost too clean, because a liquid core should be able to generate a magnetic shield, so the puzzle sharpened. Why is Mars, with a molten heart, so utterly exposed? A sea of iron. When the seismic waves came back with their timing, they carried more than just a size. They hinted at what that molten sea is actually made of. The bulk of it is iron, as you'd expect from a planetary core, but iron alone would be denser and heavier than what the measurements described. So something lighter had to be mixed in. The best fits point to a generous share of lighter elements dissolved into the metal, sulfur high among them, along with traces of oxygen, carbon, and hydrogen. That cocktail drops the density and lowers the melting point, which is part of why the core has stayed liquid across billions of years instead of freezing solid. It's a strange thing to picture, a sphere of iron thousands of kilometers wide, softened and thinned by impurities, sloshing quietly in the dark. And that exact recipe matters more than it first appears. The recipe of that molten sea held the answer to when Mars lost its shield, and losing it changed everything on the surface above. The dead dynamo. Roll the clock back about 4 billion years, and Mars was a different world. That churning iron core wasn't just sitting there, it was turning and moving metal that conducts electricity, spun and stirred by the planet's heat, works like a natural generator. Physicists call it a dynamo, and it wrapped the entire planet in a global magnetic field. For a few 100 million years, that field held. Then, somewhere around 4.1 to 3.7 billion years ago, the dynamo faltered. As the young planet cooled, the vigorous convection that powered it slowed. The churning lost its rhythm, and the field it generated weakened and finally switched off. We can read the timing in the rocks themselves. The oldest crust still carries faint magnetic stripes, frozen in like a fingerprint, while younger surfaces record nothing at all. The day the dynamo died, an invisible barrier fell, and the solar wind began stripping the planet bare. When the shield fell, while the shield stood, it deflected the solar wind, that constant stream of charged particles pouring off the sun at hundreds of kilometers per second. With the field gone, nothing turned that stream aside. It slammed straight into the top of the atmosphere, and molecule by molecule, it began tearing the air away into space. NASA's MAVEN orbiter watched this exact process still happening today, measuring atmospheric gas bleeding off into the dark. Over billions of years, that slow leak thinned a once substantial atmosphere down to the wisp Mars has now, less than 1% of Earth's surface pressure. And as the air pressure collapsed, liquid water could no longer survive out in the open. Some of it boiled off and followed the atmosphere upward, lost to the same relentless wind. But not all of it went up. Some of that water clearly escaped into the dark, but the numbers still hinted that a great deal of it had been pushed the other way, deep into the rock. Scars in the stone. When Mars still had a molten, churning core, that motion generated a magnetic field, a shield wrapped around the whole planet. As the crust cooled and hardened, tiny grains of iron-bearing minerals locked into place, aligning themselves with that field, like compass needles frozen mid-swing. They've held that alignment ever since. Orbiting spacecraft picked up the traces. Over the southern highlands, the oldest terrain on Mars, the crust is striped with bands of magnetism far stronger than anything the planet produces today. Some of these signatures are hundreds of kilometers across, and the field they recorded may have been comparable to Earth's own. The younger northern lowlands show almost nothing, so the map itself becomes a clock. The magnetized rock is ancient, the blank rock came later, and somewhere between the two, the shield switched off. The crust still carries the imprint of a shield it lost billions of years ago, a memory locked in stone, and reading it forced a hard timeline on the whole story. The Great Drying. Piece the clues together and a sequence emerges. Around 4 billion years ago, Mars ran warm and wet, with rivers carving valleys and standing water pooling in basins. Rover data from ancient lakebeds shows clays and minerals that only form when rock sits in liquid water for long stretches. Then the field faded, and the atmosphere began bleeding into space at the mercy of the solar wind. As the air thinned, the pressure dropped, and surface water could no longer stay liquid. The rivers slowed, the lakes shrank, the shorelines crept inward across hundreds of millions of years. By around 3 billion years ago, the surface had gone largely cold and arid. The transition wasn't a single event, but a slow strangling, a billion-year decline from a living-looking world to a frozen desert. By the standard story, the drying ended with a dead, empty planet, but the stray seismic signals from earlier had never gone away. Echoes don't match. Those signals came from the Marsquakes InSight had been recording since 2018. When a quake shakes the planet, its waves travel outward and bend as they pass through different materials, speeding up in dense rock, slowing down in softer stuff. By timing their arrivals, you can read the interior like an X-ray. And in one deep layer, the numbers refused to behave. The waves were moving slower than they should through solid mantle rock at that depth and temperature, not by a rounding error, but by an amount that a straightforward dry rock model simply couldn't reproduce. Researchers ran the obvious explanations first. Maybe the rock was hotter than expected, maybe the composition was off, but the mismatch held. The rock down there was slowing the waves in a way that dry stone shouldn't, so the team started asking what could be mixed into it. The slow layer. Water changes how seismic waves behave. Even a small amount, locked into the crystal structure of minerals or sitting in tiny pores between grains, softens the rock and drags the waves down. When the team ran that possibility against the InSight readings, the numbers started to move in the right direction for the first time. But so did another answer. If a portion of the deep interior was still partially molten, even a few % of liquid rock threaded through the solid, it would slow the waves too. Both explanations fit the same slow layer, sitting somewhere between 700 and 1,000 kilometers down, and neither one could be waved away. That's the trouble with a signal this faint. A soft zone deep inside Mars could mean the planet still holds heat it shouldn't, or it could mean the rock down there is holding water that never made it back to the surface. Was this layer melted, or was it soaked? And the difference between those two answers would decide the entire fate of Mars's missing ocean. A puzzle in the data. So the same recordings, the same handful of usable Marsquakes, were now feeding two very different pictures of the planet. One camp built a Mars with a warm, sluggish, deep interior, cooling slowly, still carrying leftover heat from its birth. The other built a Mars that had gone cold long ago but had swallowed its water, tucking it deep where it could still bend the waves. Neither model broke the data. That was the maddening part. Feed the same travel times in, and both came back looking plausible. because the seismometer had caught so few clean events that the margins for error stayed stubbornly wide. InSight had recorded over 1,300 seismic events in its 4 years, but only a small fraction were strong enough and clear enough to probe that depth. With the mission's clock running down, the only way forward was to go back and reread every quake InSight had ever recorded. Reopening the files. InSight fell silent in December 2022, its solar panels finally buried under Martian dust. But the archive it left behind kept working. Every wiggle that seismometer had captured was still sitting in the record, and a fresh set of eyes could ask questions the original teams never had time to. This time, they didn't lean on the quakes alone. They pulled in gravity measurements from orbiters that had circled Mars for years, mapping tiny tugs that hint at what's dense and what's light below. And they took the seismic puzzle into the lab, squeezing real rock samples under Mars-like pressure and temperature to watch how the waves actually slowed. Piece by piece, 3 independent lines of evidence started pointing at the same stretch of deep rock. Old data has a way of hiding new answers, and one team was about to pull something out of those recordings that the original models had walked right past. The depth problem. The first thing the team had to do was figure out where this odd layer actually sat. Depth is everything on Mars, because the planet changes character as you descend. Near the surface, temperatures swing wildly, and water ice can survive in the cold and the dark of the crust. Go deeper, and the rock warms steadily, until ice becomes impossible. So when the slowed waves kept pointing to a single band of rock, the location itself became the story. This wasn't a shallow feature tucked into the frozen upper crust, where you'd expect trapped permafrost. The signal came from well below that, in a zone where the surrounding stone should be far too warm to hold anything solid and cold. That mismatch is what unsettled them, a layer that behaves strangely, sitting exactly where the simple explanations don't work. The anomaly wasn't near the surface where ice lives. It was miles down, in a zone far too warm for anything frozen. 2 kinds of quakes. To read that depth, the team leaned on a quiet truth about Marsquakes. Not all of them are born the same way, and each kind tells you about a different slice of the planet. Some are triggered from above, when meteors slam into the surface and send a sharp pulse rippling outward through the crust. Those impact quakes are wonderful timekeepers. You often know exactly where and when they struck, sometimes catching the fresh crater from orbit, so the waves become a clean ruler laid across the shallow rock. But they mostly illuminate the outer shell, the first few tens of miles. The other kind comes from inside. Faults deep in the crust slip and release strain that's been building for ages, and those waves travel down through the warmer, hidden interior. Each type lights up its own layer of the world. It was the deep, tectonic quakes that mattered most, and they all seem to trace back to one restless region of the planet. Mapping the faults. When they plotted where those internal quakes were coming from, the dots didn't scatter across the globe. They clustered. Again and again, the tremors traced back to a place called Cerberus Fossae, a set of long volcanic fractures gouged into the northern plains, young enough that lava flowed there within the last few million years. That's a startling thing to find on a world we tend to picture as dead. Mars was supposed to have gone quiet, its interior cooling into stillness. Instead, roughly half of the strongest quakes InSight recorded were coming from this one scarred stretch, a place still splitting and shifting deep below the surface. A planet that keeps cracking isn't finished. Something is still driving the stress, still feeding movement into the rock. A planet still cracking at depth means heat still moving through it, and heat is exactly what would keep the buried secret from ever freezing solid. The persistent signal. When you stack seismic recordings from a single quiet lander, the noise tends to wash out, and the honest patterns rise to the surface. That's what happened here. Across dozens of separate Marsquakes, spread over more than 2 Earth years, one feature kept showing up in the deep traveling waves. It wasn't a single dramatic spike. It was subtler than that, A small, repeatable slowing in a particular band of energy as it passed through a layer far below the crust. The waves came out the other side, arriving a touch later than the models said they should, and always by a similar margin. That kind of consistency is what makes a scientist nervous rather than excited. Random flukes don't repeat with discipline. Something down there was reliably bending the waves the same way every time, so the team's first job was to prove it wasn't a ghost in the machine. Ruling out the obvious. The first suspect is always the instrument itself. A seismometer sitting on Mars swings through wild temperature shifts, from around -100 degrees Celsius at night toward far milder afternoons, and metal and electronics drift as they warm and cool. So they checked whether the signal tracked the Martian day. It didn't. The pattern showed up in quakes recorded at every hour, in every season. Next, they tested the boring rocks. Ordinary basalt, dense mantle minerals, a slightly warmer patch of solid stone, each of those can nudge a wave a little. The team ran them all, and none reproduced the exact delay, in the exact depth range, across that many events. They scrubbed for wind, for the lander's own vibrations, for errors in how the quakes were located. One by one, the mundane answers fell away, and what was left standing was an idea most scientists would once have called impossible. The team divides. A result like that doesn't unite a room, it splits it. Some on the team looked at the surviving explanation and pulled back, because the burden of proof for something that strange is enormous, and careers have been dented by claims that didn't hold. Their argument was disciplined and fair. One lander, on one spot on the planet, listening to a limited catalogue of quakes. Maybe the models were incomplete. Maybe the deep structure was just more exotic in a way nobody had bothered to simulate. Extraordinary readings, they said, need more than a persistent wobble in the data. Others pushed the opposite way. They'd eliminated the ordinary suspects, and the signal wouldn't go away. And at some point, refusing to name the obvious answer becomes its own kind of bias. The real debate wasn't happening in the press releases, it was happening behind closed doors, over whether the data was pointing at liquid. A bold proposal, so a small group put a different idea on the table, and it was a strange one to say out loud. What if the deep layer wasn't molten rock at all, but ordinary rock that had been broken and cracked over billions of years, with those cracks filled by fluid? Not a glowing pocket of magma, but a sponge, solid stone, threaded through with liquid held in the fractures. It sounded almost too tidy, and that made people nervous, but it fit the awkward facts better than Melt did. It explained why the layer could stay warm without needing heat the planet shouldn't still have. It explained why the signal sat so deep, where pressure keeps rock rigid but can't squeeze the water out of every gap. And it hinted at something the team barely let themselves say, that the fluid might be water. It was an elegant idea, but ideas mean nothing on Mars until the physics agrees, so they built the planet inside a computer. Toward the answer. Step back and look at what had piled up. An ocean's worth of water that vanished from the surface and never fully accounted for. A deep layer that stayed warmer than a cold, dead world had any right to be. And a seismic wave that slowed down in one very particular way as it passed through the rock miles below. 3 separate mysteries, chased by different people for different reasons, and they were all leaning toward the same place, not the surface, not the thin, dry crust everyone had already mapped. Somewhere deeper, in rock nobody had ever touched, where the answer to all 3 might be the same answer. If the fluid idea was right, the missing water and the warm depths and the strange wave weren't 3 problems anymore. They were one. The whole story now hinged on one calculation, and if it came out the way they suspected, Mars would never look dead again. The wet rock idea. Here's why the fluid idea could actually be tested, and not just argued about. When a seismic wave travels through rock, its speed depends on how stiff that rock is, and what fills the empty spaces inside it. Melt and water both slow a wave down, but they don't do it the same way. Molten rock softens the stone itself, dragging down both the fast pressure waves and the slower shear waves together. Water in cracks behaves differently. Liquid can't carry a shear wave at all, so those waves stumble, while the pressure waves push through the fluid almost unbothered. The gap between the two speeds opens up in a pattern that melt just doesn't produce. That split is a fingerprint. Measure how much each type of wave slows, compare the two, and you can tell soaked rock apart from cooking rock without ever drilling a hole. The signature of water-soaked rock was distinct enough to test, and the team fed the Martian numbers straight into it. Modeling the impossible. You can't fly to Mars and take a core sample, so the team built the planet inside a computer instead. They coded a slice of Martian crust and told the machine to try everything. Rock made of basalt, rock made of denser minerals, cracks packed tight or riddled with empty space, temperatures from freezing to hundreds of degrees. Each combination produced its own seismic echo, a predicted speed for the waves passing through. Run the simulation, read out the numbers, hold them up against what InSight actually recorded in the ground beneath Elysium. Match or no match. Dry, porous rock came close on one measurement and missed badly on the other. Warm, solid rock got the shear waves right, but botched the timing. Every version they tried left a gap they couldn't close. Model after model failed until only one family of solutions survived, and every one of them was wet. The numbers converge. One good result is a coincidence. What the team had was 3 separate methods, each blind to the others, each landing in the same place. The seismic velocities said the deep rock behaved like stone with liquid in its pores. The gravity measurements, mapped from orbit, showed the crust was slightly less dense than solid rock should be, exactly what you'd expect if the fractures were filled rather than hollow. And the mineral physics, the lab-measured behavior of rock under crushing pressure, drew the same line without being asked. Seismology, gravity, and the physics of minerals don't share notes. They come from different instruments, different physics, different teams. When separate methods that can't lie all agree, the resistance collapses. And in 2024, the team finally said out loud what they had found. The hidden reservoir. Buried in the Martian crust, somewhere between 11 and 20 kilometers down, sits a layer of rock shot through with cracks. And those cracks are not empty. They're saturated, filled with liquid water, held in the pore spaces of fractured stone, the way water fills a wet sponge. Not ice locked in the poles, not vapor drifting in the thin air. Liquid water, deep underground, kept warm enough by the planet's own heat to stay a fluid across billions of years. The strange thing beneath Mars was the one thing everyone had stopped expecting to find there. InSight never set out to look for it. A seismometer listening for quakes had, without meaning to, mapped a hidden reservoir miles below the surface. Confirming the water was only the beginning, because when they estimated how much of it there was, the number stopped everyone cold. An ocean's worth. When the team ran the seismic velocities through their models, the water they were describing wasn't a trickle threading through cracks. It was a layer, saturating the fractured rock across a band of the crust so wide that the totals kept climbing past anything they'd braced for. Pull all that trapped water out, spread it evenly across the whole face of Mars, and it wouldn't make a puddle, it would make a sea. The best estimates put it deep enough to drown the entire planet under something like a kilometer of water, maybe more, a global ocean wrapped around a world that today looks bone dry from orbit. And the strangeness wasn't just the size, it was the recognition that came with it. That volume was hauntingly familiar, because it was roughly the size of the ocean everyone had spent decades trying to find. Where the ocean went. For years, the missing water had a tidy explanation. Mars lost its magnetic field, the solar wind stripped its atmosphere, and the oceans boiled off into space one molecule at a time. The isotope ratios seemed to back it up. The water went up, and it was gone. But the deep signal told a quieter, stranger story. Some of that ancient sea may never have left at all. Instead of rising into a dying sky, it soaked downward, seeping through fractures into the warm rock below and settling there while the surface froze and the winds did their slow erasing overhead. The great escape everyone imagined might have been, in part, a great descent. Mars hadn't lost its ocean at all. It had simply swallowed it and put it somewhere no drill on Earth could reach. Miles down. That last part is where the wonder turns cold. The models don't place this water in some shallow layer a few meters down. They put it roughly 11 to 20 kilometers beneath the surface, locked inside cracked rock under crushing pressure and rising heat. To grasp what that means, look at our own record. The deepest hole humans have ever drilled, the Kola super-deep borehole in Russia, took about 20 years and reached just over 12 kilometers before the heat softened the rock and the project stalled. That was on Earth, with everything we had, right outside the door. Now imagine attempting it on another planet, across tens of millions of kilometers, at the bottom of a gravity well, with a fraction of the power. The reservoir might as well be sealed behind stone. And yet the very thing that makes it unreachable makes it interesting. It sits far too deep for us to touch, but that same depth is exactly why it might not be empty of life. Not frozen but liquid. Down there, the rules change. On the surface, water freezes solid, but the Martian interior still holds heat left over from its formation and from the slow decay of radioactive elements in the rock. That warmth doesn't need to be dramatic. It only needs to keep the temperature above freezing, and several miles down, it does. Pressure does the rest. Squeeze water hard enough, and it stays liquid at temperatures that would turn surface ice to stone. The deeper you go, the more the weight of the crust above holds those molecules in a fluid state, tucked into the pores and fractures of the rock. And there's a third gift hidden in that depth. Miles of stone sit between this water and the brutal radiation that sterilizes the Martian surface, a shield no lander could ever build. Liquid, warm, and sheltered from radiation is a description that on Earth means one thing above all others, an address where life could persist. The habitable deep, that single word, persist, is what changes the stakes. For decades, the search for Martian life has chased fossils and dry lake beds, the memory of water rather than the water itself. A stable, liquid, shielded reservoir is something different. It isn't a place life used to be, it's a place life could still be. Stability is the quiet hero here. The surface of Mars swings through wild temperature extremes and lethal radiation, but a deep aquifer barely notices the seasons passing overhead. Conditions that hold steady for millions of years give slow chemistry the time it needs to become slow biology. So the question stops being whether Mars was ever habitable and becomes whether it still is, right now, far beneath the dust. This isn't wishful thinking, because on our own planet there are living worlds hidden just as deep in exactly these conditions. Life underground. Drill into the bedrock beneath your feet, and you don't reach lifelessness. You reach a hidden biosphere. Microbes have been pulled from mines and boreholes more than 3 miles down, living in water trapped inside solid rock, some in pockets sealed off for millions of years. They survive on nothing we'd recognize as food. No sunlight reaches them, so instead they feed on chemistry, harvesting energy from reactions between water and stone, from hydrogen and iron and sulfur. Some divide so slowly that a single generation may take centuries. They aren't thriving so much as enduring. By some estimates, this deep biosphere holds a huge share of all the microbial life on Earth, an entire living realm we never see. It runs on exactly the ingredients we suspect are waiting under Mars: water, rock, warmth, and time. If life ever started on the young, wet Mars, the deep reservoir may be the one refuge where it could have ridden out the apocalypse above. The trapped question. So here's the strange position we find ourselves in. The radar and the models point to water sitting somewhere in the mid-crust, maybe warm enough to stay liquid, maybe holding the chemistry life needs. And every bit of it is sealed under solid rock, the kind you can't dig through with a shovel or a rover arm. The deepest anyone has ever reached into Mars is a few centimeters, scratched by a drill on a lander that struggled just to break the crust. The reservoir we're talking about sits far below that, past the reach of anything we've flown, anything we've landed, anything currently on a drawing board. It's a peculiar kind of frustration. We can map it, estimate its volume, argue about its temperature, and still not touch a single drop. Knowing something might be alive down there and being able to reach it are two very different problems, and the second one is brutal. Beyond our reach. Think about what drilling that deep would actually demand. On Earth, the deepest borehole ever cut, the Kola Superdeep, took about 20 years to reach roughly 12 kilometers, and that was with a full industrial rig, unlimited power, and a crew standing right there. The Martian water may sit somewhere in that same range, kilometers down through cold, hard crust. Now strip away the crew, strip away the power grid. You're left with a machine that has to fly across 200 million kilometers, land intact, generate its own energy, and then bore through solid rock for years without a single hand to fix it when a bit snaps or a motor stalls. No robotic mission has ever come close to that. The gap between what we can send and what this would take is measured not in upgrades but in generations of engineering. We may not be able to drill to it for generations, but there might be other ways the planet itself brings its secrets closer to the surface. A different Mars. Step back for a moment and look at what this does to the whole idea of Mars. For decades, the picture was simple. A dry, dead rock, its water long gone to space, its story finished billions of years ago. What's emerging instead is a layered world, a frozen, radiation-scoured surface on top. Below that, cold crust. And deeper still, a hidden zone where liquid water may persist in the pores of the rock, warm, stable, quietly untouched by the catastrophe that stripped the world above. That changes the question entirely. Mars stops being a corpse and becomes something closer to a sealed vault, most of its interesting chemistry hidden where we can't easily look. Once you accept there's water locked deep in the crust, a series of older, dismissed Martian mysteries suddenly start to line up. The other signals. For decades, Mars kept dropping small hints that water hadn't entirely left. Spacecraft mapped ancient riverbeds carved into the highlands, deltas fanning out where lakes once stood, minerals that only form in the presence of liquid. On their own, each clue felt like a fossil of a wetter past, evidence of what Mars used to be, not what it still is. But the deep crust finding recasts those clues. If the water never escaped to space, if it soaked down into the rock instead, then the surface features and the buried reservoir are two ends of the same story. The rivers didn't just dry up, they drained. And there's one hint that always sat uneasily with the dead planet picture, coming not from ancient terrain, but from something detected right now, deep under the ice. Years before InSight, another spacecraft claimed to have found liquid water under the pole, and that claim had started a fight of its own. Debate at the pole. The spacecraft was Mars Express, in orbit since 2003, carrying a radar instrument called Marsis. It sends radio pulses down through the south polar ice cap and listens for the echoes that bounce back from whatever lies beneath. Different materials reflect that signal differently, and by 2018, the team saw something that stood out sharply from the surrounding rock. About 1.5 kilometers down, one patch reflected the radar far more brightly than the ice above it. On Earth, that kind of strong, sharp echo is the signature of liquid water sitting under a glacier. The researchers announced what looked like a buried lake, roughly 20 kilometers across, hidden beneath the frozen cap. Later passes hinted at more of these bright patches, a scattered network of possible pools rather than a single body. For a while it looked like proof of Martian lakes, but then other scientists offered a colder, more mundane explanation. Consensus and doubt. The problem was the temperature. At that depth beneath the pole, models put the rock well below freezing, cold enough that any pure water should be solid. To stay liquid, it would need to be an extreme brine, loaded with salts, and even then, some estimates said it wasn't quite cold-tolerant enough without an extra heat source no one could identify. So teams went looking for other things that could throw back a bright radar echo, certain clays, frozen brines that aren't actually liquid, layers of iron-rich minerals arranged just so. Follow-up studies showed that several of these mundane materials could mimic the exact signal the lake claim rested on. The detection wasn't debunked, but it wasn't confirmed either, and the field settled into an uncomfortable stalemate that still hasn't fully resolved. Whatever the polls turn out to hold, the deep reservoir doesn't depend on them, and confirming it will take a new kind of mission entirely. What it would take. Confirming the deep reservoir means going back to Mars with better instruments than InSight ever carried. The 2018 lander sensed the interior with a single seismometer, and even that lone ear picked up faint hints of something wet far below. To turn a hint into a map, you'd need probes that can read the crust at greater depth, and models refined enough to tell water apart from warm rock or fractured stone. Engineers have sketched drills that could reach further than any that has touched another world, and orbiters carrying radar tuned to look kilometers down rather than skimming the surface. Each piece already exists in some early form. The challenge is fitting it onto a spacecraft, landing it in the right place, and keeping it alive through the Martian cold long enough to listen. None of it will happen quickly, and that raises an uncomfortable question about how patient we're willing to be. The search sharpens. A single station can tell you that a Marsquake happened and roughly how the ground shook, but it can't tell you exactly where the water sits. For that you need triangulation, the same trick we use on Earth. Several seismometers spread across the planet, each timing the same tremor as it arrives, and the differences between those arrivals draw lines that cross at a single point deep below. Set up a dozen listening posts across the Martian surface, and the vague signal that came from one becomes a precise depth, a shape, a location you could aim a future mission at. The interior would stop being a blur and start becoming a map. We'd finally know not just that the water is there, but where and how much. One year on Mars gave us an ocean's worth of mystery. Imagine what a dozen could reveal, and why some scientists say the real payoff is what it means for us. A question of life. Everything about this reservoir circles back to one word: water. On Earth, wherever we find liquid water, we find life, clinging to it. In deep mines, in scalding vents, in rock kilometers below the surface where sunlight never reaches. If Mars has held liquid water in its crust for billions of years, then it has held one of the conditions life needs for just as long. That doesn't prove anything is alive down there. But it moves the question from whether Mars could ever have supported life to whether a refuge for it still exists, sealed away, waiting. A planet we've long called dead might simply have folded its living chapter underground when the surface turned hostile. The answer to that question wouldn't just change Mars, it would change how alone we think we are. The long wait. Here's the hard part about a discovery like this. Confirming whether anything lives in that buried water isn't a matter of pointing a better camera at Mars. It means landing a machine that can drill through more than a kilometer of rock and ice, in a place with no roads, no crew, and a signal delay that can stretch past 20 minutes each way. Nothing we've built for Mars comes close to that reach yet. The deepest we've ever dug into another planet is a few centimeters of scraped soil. A mission designed to touch water that deep would take years to plan, years to fly, and years more to work once it arrived. So the honest timeline isn't next year, or even next decade. It's the kind of question a scientist might hand to a student who hasn't been born yet. We may not live to see the drill reach the water, but the discovery has already handed us something we didn't have before. Reflections in red. For most of human history, Mars was the definition of a lost cause. A rusted world, cold to the bone, its rivers gone dry billions of years ago. We named it after a god of war and treated it like a tombstone in the sky. And the whole time, if the readings hold, it was keeping a secret in the dark under its own crust. Enough water, some estimates suggest, to cover the entire planet in a global layer more than a kilometer deep, hidden where no telescope could ever see it. That reframes the planet completely. Not a dead thing, but a quiet one, sitting on a reservoir it never fully surrendered. There's a strange comfort in learning that Mars kept its water after all. But there's also a warning buried in the same fact. The warning below. Because Mars didn't start this way, it once had rivers that carved canyons, standing lakes, maybe an ocean across its northern lowlands. It had a thicker atmosphere and a magnetic field wrapped around it like a shield. Then the core cooled, the field faded, and the solar wind began stripping the air away, molecule by molecule. The water that couldn't escape retreated downward, sinking into the crust until only that deep, hidden layer was left. What remains on the surface today is a memory of a world that was once far more alive. None of that happened in a single catastrophe. There was no impact, no explosion, no moment you could point to and call the end. Everything Mars lost, it lost slowly and invisibly, which is exactly what makes the comparison to our own planet so hard to look away from. A mirror for Earth. Earth runs on the same machinery Mars once had, a molten iron core spinning fast enough to generate a magnetic field, that field wrapping the planet in a shield that deflects the solar wind before it can strip the air away. Mars had all of it once, and then the core cooled, the field faded, and the atmosphere thinned until the water had nowhere left to stay on the surface. We tend to picture planetary death as something violent, a collision or a burst of radiation. What happened to Mars was quieter than that. It was a slow settling, a balance tipping degree by degree over hundreds of millions of years, until a world that held oceans became a world that holds its water locked kilometers underground. None of this predicts anything about our own timeline, and it isn't a warning that Earth is next week's headline. It's just that Mars shows us what the far end of that slow process looks like. But knowing the water is down there and reaching it are two different problems, and one of them may be impossible. The unreachable water. The reservoir the seismic data points to sits somewhere between 11 and 20 kilometers beneath the Martian surface. Above it lies a crust of rock, frozen solid for billions of years. Nothing humanity has ever landed on Mars has gone deeper than a few meters. The deepest drill we've flown, on the InSight lander, was designed to reach 5 meters, and it got stuck at about 40 centimeters. To confirm liquid water directly, you'd need a machine that can bore through kilometers of cold basalt, survive the pressure and heat as it descends, and do it all remotely on a planet where help is months away. No such machine exists, and no current mission proposes to build one. So the discovery arrives with a strange kind of distance built into it. We can measure the water's echo, model its depth, argue about how much is there, and still stand no closer to touching it than we did before. Because if that water is liquid and warm and shielded from everything that killed the surface, then it is exactly the kind of place we have spent decades learning to ask one question about. If anything still lives, on Earth, life doesn't stop at the surface. It goes down. Microbes live in rock 5 kilometers beneath our feet, in gold mines and ocean floor sediment, cut off from sunlight, feeding on chemical energy pulled from the stone and the water around them. They don't need the sky. They need liquid water, an energy source, and shelter from radiation. The deep Martian reservoir, if the readings hold, would offer all three. Liquid water kept warm by the planet's remaining internal heat. Chemistry between rock and water that could feed the same kind of metabolism. And kilometers of crust blocking the radiation that scours everything above. That is not a discovery of life. No one has found a cell, a fossil, or a chemical signature down there, and nobody honest is claiming otherwise. It's only that the one place on Mars we can't rule out happens to match the conditions life uses to survive in the dark on our own world. For now, all of it stays sealed beneath the rock, and the story of Mars ends not with an answer, but with a place we know exists and cannot yet visit. Where it stands. So step back and look at the whole shape of it. A planet that once ran hot enough to power a magnetic field, that shield failing as the core cooled and the dynamo went quiet, the solar wind stripping the air away, molecule by molecule, over hundreds of millions of years. The rivers dried, the ocean that may have covered a third of the northern hemisphere thinned, froze, and vanished from view. Some of it escaped to space, some locked into ice at the poles, and a share we couldn't account for went missing entirely. Then a single lander sitting in Elysium Planitia caught what the telescopes and orbiters never could. A faint drag in the seismic waves, a delay of a few seconds where none should be, pointing to fractured rock, a good 7 to 12 miles down, holding enough liquid water to fill an ocean. That's where the science rests today. Not proven, not settled, but measured and modeled and hard to explain any other way. If a story like this one holds your attention, there are more waiting on the channel.